Good morning, everyone. It's a pleasure to see so many familiar and new faces here. So as Matt was saying, the plan is to start a bit slow and kind of for this workshop, the first 2 days we're going to have tutorials. It could be a nice way to introduce people who have known some ideas, some concepts in causal inference to the deeper mathematical theory. And it could also serve as a good refreshment for people who already know a lot. I will just start with something quite non-technical. There won't be much math in it. Just to get you warmed up for all the nice things that will come. So originally the title I wrote, Origins of Randomization for Causal Inference. You will see this is largely based on the talk I previously gave in another occasion. Then I thought when I'm preparing this talk, I thought I should probably say something about the future and also where we are, how the history connects to the present and the future. So I added this, the rise of design. So randomization is an old idea. It's one of Fisher's first principles for experimental design, and has really a big consequence for how the modern science is being done. So for those of you who come from a health science background, you will know how important randomized clinical trials are viewed in that field, and how much of an effort has been taken by regulatory agencies to ensure that it's done in a rigorous way. So randomization can already be found in Fisher's book in 1925, The Statistical Methods for Research Workers. The first paper that actually proposed kind of randomization as a systematic principle is this paper in an agricultural journal in 1926, so exactly 100 years ago. Then there's obviously his famous book, Design of Experiments. So we take this idea for granted, but this is not always the case, even after this idea was introduced. So this is an interesting quote from William Gossett, aka student, who developed the student's t-test. He repeatedly disagreed with Fisher. So they were good friends, but in proofreading this Fisher's book, he wrote something which is quite interesting. He said that you would want a large lunatic asylum of the operators who are apt to make mistakes enough even at present for this idea to be somehow acceptable. So there was a lot of pushbacks against these ideas at the time. So this is Fisher in 1958. So as I mentioned, this talk was, I started with Fisher, and this is because the talk was based on a previous talk given at the Fisher in the 21st Century Conference organized by the Granville and Keith College, where he was a student and a fellow, and there was a controversy about his involvement in eugenics. So college organized a conference in 2022. So that talk was largely based on two review articles of this history of randomization. There's one by his daughter, John Fisher Box, who wrote the biography for R.A. Fisher, but also this is a very nice shorter article that focused on design of experiments. There's another really nice history of science article by Ian Hacking that I found, which is fascinating and talks about all the origins of randomization, even before Fisher. My idea is to base the talk on that, but also talk about the rise of design to connect with current research. And the talk might still be too Fisherian, and that's not always very good because he was a very controversial figure. So I don't want to be seen as agreeing with everything Fisher ever said. Something I will probably look to improve in the future. But this talk, I'll mention Fisher a lot because he was really significant in the development of this idea. And we do these historical searches because it would help, I hope it would help us understand what we're doing now and what we ought to do in the future. Okay, so this is a photo of Ian Hacking, which I've never met, and he passed away 2 or 3 years ago. But I felt that this talk owe a lot to his work. He's a great philosopher of science. So for the first part, origins of randomization, how I want to structure it is to follow these list of roles of randomization in a paper by David Cox. He wrote this review article in 2009. I found it was really insightful. So he basically said randomization has kind of 3 unique roles. The first is to avoid selection and other biases and do so in a publicly convincing way. Second is to provide a unified approach to the analysis of many standard designs. Third is to provide a basis for exact tests of significance and related interval estimates. So I'll walk through these points and then discuss a few other related topics about randomization. So the first idea was randomization helps avoiding hidden bias. And this you can find in these early experiments in psychophysics. So the first randomized experiment that we know was done by Charles Sanders Peirce and his student Jastrow in 1884. And this was in psychophysics. It was a period where people wanted to really understand, I guess, how the limitation of humans' mind. So this was an interesting experiment. They want to test if there's a threshold of the human sensation of pressure. And the way to do it is they ask an experimental subject to experience a weight of 1 kilogram, and then a second weight that's slightly heavier or lighter, and whether that's heavier or lighter is randomly decided by a well-shuffled card or a deck of cards. So this type of experiments are done in psychophysics, in psychology, from that period. There was another example by I think this is a French psychologist, where he kind of was interested in the power of telepathy. And then he have an agent draw a random playing card and then concentrated upon it for a time with the idea that try to get that number and the suit to another one sitting across the room. And then you have that reagent guess the suit of the card. And then this was done in a more kind of, in a better way perhaps, as to not only randomize the card, but also whether the trial would be a regular or control. Control meaning that actually the agent did not actually look at the card at all. So they wanted to create that contrast. So there are all these interesting ideas of randomized experiments in psychology. Another kind of practical application was in medicine. So Bradford Hill was famously kind of involved in pushing randomization in medicine. And he eventually persuaded the Medical Research Council in the UK to launch 2 randomized control trials in 1946. So those were the first randomized clinical trials that we know. So the psychologists Fisher and Hill, they all emphasized how randomization eliminates personal idiosyncrasies and confounding bias. So this is a quote from the Design of Experiment book, where it says, randomization properly carried out relieves the experimenter from the anxiety of considering and estimating the magnitude of the innumerable causes by which his data may be distributed, may be disturbed. So this argument you will still find routinely being used by people to justify randomized experiment, especially to a non-technical audience. And also this is similarly used in observational studies that are designed to emulate a randomized experiment. Okay, so that's the first role. It's sort of not so technical, not too involved, but it's still quite powerful. The second argument was statistical, and this I learned really from David Koch's review article. So I think the origin of this is always that Fisher kind of thought about randomized, or statistics rather, in a quite geometric way. So one of the first breakthrough results he proved, this was just I think a few years after he graduated from his bachelor's, was just a proof of the student T distribution using a geometric argument. It's quite fascinating because now we know the student T distribution and all that, and we thought student T derived everything. But he actually guessed the PDF of the student T distribution just using a few moments of the distribution. He didn't actually derive it. So Fisher gave a proof of like that's actually the right density function, and his argument was based on this picture essentially that represents n observations as a point in the n-dimensional space, but then in a T distribution you're testing for the mean, so you're kind of constraining the mean. So then he said it's basically you're given the sample mean, then this point must lie on a sphere in the n-1 dimensions. And I think mu1 is just the sample variance. So that's the kind of the way he kind of thinks about a lot of the statistical problems, and it is repeatedly used by him in the next decade and how we teach the theory of normal linear models today. Leading up to randomization and sort of analysis of randomized experiments, so Fisher kind of already pointed out this idea in this paper in 1923, where I think this is where usually when people say the analysis of variance was first proposed, and then you already said that you have to randomly write down some numbers. And then in the 1926 paper, this is where I mentioned earlier, this is he kind of said quite clearly that the one way of making sure that a valid estimate of error will be obtained is to arrange the plots deliberately at random, and blah, blah, blah. So here you can see the difference between the first row, which is just avoiding bias. Here the emphasis is on validity of the statistical inference and correctly quantifying the statistical error. So how that's done is, Yao will tell you about that in a moment, but there is like a strong geometric intuition in this work. Nowadays, when we teach ANOVA, we do this under the normal linear model and everything works out beautifully. But Fisher was actually convinced that those assumptions are not needed with randomization. I found this really interesting quote from this paper by his daughter, and the quote is, so his confidence in the results, however, depended on the geometric interpretation as was then second nature to him. He could picture the distribution of n results as a pattern in an n-dimensional space, which is what we described earlier. And he could see that randomization would produce a symmetry in that pattern rather than that produced in a pattern rather than like that proposed by the kaleidoscope, and which approximated the required spherical symmetry available, in particular from standard normal theory assumptions. So this really took me as a surprise, because I thought I have no idea that this is actually the intuition. The intuition was the randomization created that symmetry in that sphere we mentioned about those points that then allows us to kind of say that's approximately normal, because the normal distribution would be uniform on that sphere. So a little bit of technical things about this. So essentially what Fisher was describing, or his daughter was describing, this randomization distribution. So the idea is that you introduce some randomness by the experimenter artificially. I'll call that Z, and I'll call W everything else in the world. Potential outcomes, if you prefer that, but everything else basically. So the randomization distribution is just a distribution of a statistic T, which is a function of the randomization Z, and everything else you observe or you conceptualize, but that's conditional on everything else. So you only look at the randomness generated by the experimenter, and you look at that distribution. That's what the kaleidoscope is kind of trying to describe. So all the randomness stem from the experiment, and that's why it has all these nice model-free properties that Yao will discuss, because that's the randomness you introduce as experiment. So you should have good control and good understanding of where that randomness comes from and how that is modeled. So in the model in theory, this W, everything else, would include all the potential outcomes of the experiment and any pre-intervention variables. And these variables are required, especially if they're used in the randomization. So I wanted to draw a quick discussion here on this setup with a criticism that sometimes people make about the idea of potential outcomes, because often in the literature these are described as fixed quantities, which are a little bit unsatisfying from a metaphysical point of view. That seems everybody has their fate decided. So Philip David made a point about this in his 2000 JASA paper. But if you look at the mathematical theory, this interpretation is actually unnecessary. What's really kind of the key idea is you condition on these potential outcomes. And so you don't really need to say what the potential outcomes, what the nature are. Do they actually exist in the world? Are they just a kind of imagination in our head? Okay, so here's an example of randomization distribution. So a simple example is just consider this kind of difference in means statistic in an experiment that randomizes n1 units to the treatment, so that's Zi equals to 1, and n0 unit to the control, so that's Zi equals to 0. So if I let y dot represent all the potential outcomes for this experiment, and I'll call that potential outcome schedule, which is a terminology from David Friedman. So the idea is we want to calculate the distribution of beta hat given all the potential outcomes. So this is done basically by Neyman in his 1923 paper, as we know it. Neyman computed the expectation and variance in this randomization distribution that's given in the screen. So this result is very well known. Before I kind of say a little bit about how these results can be derived, there are a few interesting historical notes. So Neyman thought the potential outcomes model was a novelty at the time, but he strongly kind of objected the idea that he anticipated Fisher's use of randomization. And this is a kind of a paragraph from his biography that he really kind of emphasized that so Neyman said he kind of treated the problem theoretically, and the potential outcomes were kind of introduced as a mathematical way of describing his calculations. But the point that connects randomization to the kind of the physical act and how that justifies statistical inference in the real world, that was a contribution of Fisher's. And the second note I wanted to make is when I was studying causal inference myself for a long time, I somehow had this mental picture that Neyman had this idea of potential outcomes in 1923, and nobody knew about it. And then this was kind of brought back by Don Rubin and others in the 70s and 80s. It's like this gap. But actually, people have continued to use this model in theoretical analysis of randomized experiments, like this paper by Welch and also the work by Kempthorne. But importantly, that line of work was kind of continuing just as a theoretical investigation of the model, not much said about the real world. So in that sense, Rubin did make a very different point about the importance of formalizing these potential outcomes, not just for randomized experiments, but also for observational studies. So that's Neyman when he was young. I wanted to say something about how these results are obtained because I found a beautiful proof in David Cox's paper. So if you look at like a standard textbook proof of Neyman's results, such as the one in Imbens and Rubin, that takes 5 pages and a lot of algebra. So Cox gave a really, in my opinion, much better, more elegant proof of this. And he actually did this for a more complex randomized block design and in just half a page. And his argument was more or less the following. He said basically, if we just consider the simple case of simple randomization, he said, well, first look at the variance of this quantity. So we know beta hat is a linear function of the potential outcomes. So the variance must be a quadratic function of the potential outcomes. Then he had a kind of a symmetry type of argument. By permutation invariance and considering some special cases, you can arrive at this formula where the variance must be kind of some constant times s0 squared as some constant times s1 squared minus some constant times s01 squared. And those constants needs to be decided. And then to decide those constants, what you can do is to consider a model where the potential outcomes are jointly their IID and for each individual they're bivariate Gaussian. And then from the bivariate Gaussian, you actually get 2 variances and 1 covariances. And if you do that calculation, that gives you these 3 constants. And so it's a very beautiful proof, and also kind of resembles that Fisherian way of thinking of the symmetry on the sphere. So I really like that. So I talked to Xingyuan Li when I visited Chicago last year. I told him that, do you know this proof by David Cox? Because Xingyuan is a kind of expert in randomization tests. And then he said, we might have rediscovered this in another paper without knowing this at all. So that's telling us that there's actually perhaps a lot of good ideas in the design of experiments literature that's not yet kind of being well understood in the modern framework of causal inference, perhaps. Yeah, so that's David Cox. He was 90, a few years after he wrote that review article. So the third role that Cox mentioned was giving a basis for exact tests. This is what we know as randomization tests. So Fisher articulated this point in his Design of Experiment book. He said sort of the physical act of randomization affords the means of examining the wider hypothesis in which no normality of distributions is implied. So he actually demonstrated this randomization using a test in a pairwise randomized experiments. This is from agriculture, I think. And then he was enumerating all possible scenarios of the randomization. And then he did some calculation in this table, and he found that the randomization p-value is 0.053, which is probably where also a lot of these the scene of 0.05 in the sort of the crisis of hypothesis testing we're seeing today come from. But his point in that example was that this p-value was very close to the p-value of a t-test. So this is again trying to say that randomization keeps you a way of using analysis of variance and the t-test without the normality assumption. So that's kind of his argument in the Design of Experiment book. So Yao will go a little bit further into this type of argument in the next session. So that's kind of the role of randomization in experiments. One more thing I wanted to discuss, which isn't available in these review articles, but I think it's very interesting, very important, and I kind of learned a lot about this from George Davis Smith, was there's a very strong interplay between genetics and statistics in this development. So Fisher is one of the three primary founders of population genetics, the other two being Sewell Wright and JBS Hoden. So you can see how there's a very strong interaction between Fisher's interest in genetics and statistics. For example, this Fisher 1918 is a very famous paper in genetics where he talks about the genetic similarities between relatives and how you can use that to calculate the heritability of a trait. This is actually also very important for statistics because this is the first time the term variance was coined. Because at the time, there was various ways to quantify the statistical error. You can use, most people use standard deviation or something like that. But Fisher's observation was that variance is additive with respect to addition of independent random variables, so that makes it amenable to a lot of nice analysis, basically leading to the analysis of variance. So the concept kind of comes from Fisher's analysis of genetic data. Another very strong hint was in this this article. This was a speech he gave to a group of geneticists. But there he talked about connections between our two subjects, which is statistics and genetics. He said the factorial method of experimentation, now of a lively concern so far field as the psychologists or industrial chemists, derive its structure and its name from the simultaneous inheritance of Mendelian factors. And Mendelian factors is what we call genes these days. Right? So he kind of, when he was thinking about these experiments for agriculture, there was a lot of ideas that he just imported from genetics. So that makes a curious case for whether the whole randomization for experiment was actually also derived from genetics. And this is not very clear after I tried to investigate a bit into the literature. There are some hints that there's probably a connection. For example, there's a very interesting kind of article by George Bernard. It's he kind of emphasized how big a role that the genetics theory played in the development of statistics and probability. He said Mendel's theory was the first in natural science to express its experimental predictions in terms of exact frequency probabilities. I thought this is actually kind of important, because when we learn probability theory, we always thought, oh, okay, there's some gamblers in the 17th, 18th century who kind of first discovered probability, which is true. And then there are obviously these in astrophysical experiments, Gauss, Legendre, and others, they've kind of done the least squares. But actually in natural science, and that's also where statistics kind of become prominent, that's when randomization and also when Mendel's genetics was kind of first developed. Because that's the first kind of example in natural science where chance really plays a critical role. If you think about physics, well, maybe statistical physics, there's that, but still you're interested in macroscopic information. But it really, in this genetics, this is where you have to deal with science, you have to deal with chance, and you have to find a scientific way to deal with chance. And that's so it's not a surprise that in the kind of the beginning era of statistics, there was a lot of people who were working on genetics and statistics at the same time. So in Fisher's 1952 speech, he also talked about this sentence: the different genotypes possible from the same mating have been beautifully randomized by the meiotic process. So it just makes you wonder that, gosh, he must have, like, this randomization idea must just been there so deep in his mind that when he saw these agriculture experiments, he thought, well, why don't we just randomize? So another point I wanted to kind of make, which kind of supports that theory, is that obviously we have a heritage from that era, not just from randomization tests and inference, but also of these graphical diagrams. So these graphical diagrams for causal effects were first introduced by Civil Wright in a series of papers around 1920. So the main purpose of this originally was to understand genetic heritability. So Civil Wright, in this is a figure from this paper where Civil Wright was looking at the relative importance of heredity and environment for guinea pigs, and he drew this very nice diagram, and from here he developed all his past analysis. And today we look at this in a much more general way. And one point I wanted to make is there's a remarkably similar argument made by Wright when he was defending his causal graphs. So in a reply to criticisms, Wright wrote the following. So he said, the most satisfactory applications are naturally those in which a complete system of causal relations is at hand. Niles, who criticized his approach, Niles dismisses the validity of the results in a paragraph already quoted on the grounds of a basic fallacy in the assumption that it is possible to set up a priori a comparatively simple graphical system, which will truly represent the lines of action of several variables upon each other and upon a common result. So you can kind of see that, I think, today, even in the debates about graphical models in how we use it, that we say, well, does it actually capture everything in the system? Is it actually too much of a stretch? Then later on in that reply, Wright says to defend his the causal interpretation of his results, he said it was of course realized that the concrete phenomenon actuality, I think that's just kind of what he was meaning about causality, of the results was not proved by the analysis by past coefficients. This rests on the validity of the premises, that is, on the evidence for Mendelian heredity. So essentially, in my words, he would basically saying the fact that he was doing causal inference is not because he was using his past analysis methods. It's because there was this Mendelian randomization that's happening. And that's remarkably similar to what Fisher was using in his argument. And to some extent, this paper is obviously before Fisher's papers. So he kind of have kind of recognized that importance of randomization for causal inference before Fisher. But this is obviously in a very specific context about genetics. I thought I would just connect a little bit with my own work. I wrote this paper with George David Smith and a student we co-supervised where we developed this method called almost exact Mendelian randomization. And this in some ways combines the insight of Fisher, Wright, and Houdan. So what we basically did is we drew a complex diagram, this kind of graphical diagram for meiosis, which is kind of largely studied by Houdan. And then we use these graphs, which are from Civil Wright. And the idea is to use these to select instrumental variables and then do randomization inference, which is the idea due to Fisher. And Wright was already using what we now call acyclically directed mixed graphs. So these are graphs with directed edges and also bidirected edges, so with arrowheads on both ends. So he actually had a remarkably clear description of what this graph is intended to describe in this paper. He said those variables which are treated as dependent are connected with those of which they considered functions by arrows. So this is kind of basically saying things that are causal are represented by a directed edge. Then he said a residual correlation between variables is represented by a double-headed arrow. For some time I was really thinking about what these graphs mean. Then I read this, and I thought, why don't we use a simple definition of causal ADMG models in a non-parametric setting by basically getting these concepts about basic consistency as an axiom with respect to the directed edges, and then the basic single-world independence as an axiom with respect to the bidirected edges. So I wrote a paper last year about this, and recently I realized that this model is equivalent to the causal model defined by the potential outcome calculus, which is equivalent to Pearl's celebrated dual calculus. So what I'm trying to say is that you can define the causal ADMG model in an axiomatic way by basically translating Civil Wright's definition to a non-parametric context with potential outcomes. And that model is exactly equivalent to the model where potential outcome calculus can be applied. So if you that's basically saying potential outcome calculus is complete for this definition of the causal ADMG model. So that's a picture of Civil Wright. Okay, so that's kind of my first part of the talk, where I've mostly discussed randomization. The second part of the talk, I wanted to kind of connect a little bit more of what's been done since Fisher's time and of today, and also maybe what we can all look at during this program is what I call the concept of design. So for Fisher, there's a very interesting article he wrote that he kind of reflected on how his view shifted, because he basically came to Cambridge as an undergraduate student. He got into eugenics, genetics at the time. He did a lot of work. Then in 1918, he wrote that famous paper that's kind of a classic in genetics, at least nowadays. But then that's also the paper that got him into trouble with Carl Pearson, because Carl Pearson didn't like this way of doing genetics, I guess. Then he actually couldn't find a job. Then it was a coincidence that he was offered a job by the Rothamsted experimental station that has an enormous record of agricultural data, and they needed a data scientist to analyze that record. So then Fisher did all the MLE, that kind of business, but it was all very quantitative. But during the time that he was at the Rothamsted experimental station, employed as a statistician, his kind of idea changed quite a lot from just solving those mathematical problems into the somehow design of experiments as the basis for science. And he reflected that in this article. He kind of basically said, he has this idea of maximum likelihood being the most efficient estimator. So that kind of uses all the information in the data. Then at that point, it seems that then we don't need statisticians anymore or data analysts anymore, because you have a way that automatically uses all the information in the data. So why do you need everyone else to be any human input in this? But then he made this very interesting discussion. He said, this finding, which is about randomization, this finding shifted the moral balance. His business became much less like of a conjurer who is expected to work wonders, and more like that of a chemist who undertakes to assay the proportion of gold in a sample. The weight in his responsibility was thrown back onto the process by which the data had come into existence. So Fisher was describing how his view changed from just being an analyst to someone who is in active control of the whole process, and especially in the process of how the data is collected. So as one example is this famous technique introduced by him for experimental design called blocking. This is obviously the name kind of come from the agricultural experiments, but the idea is to basically create groups of units with similar background attributes and then randomize within the group. So this has a number of advantages. It allows us to eliminate a lot of the idiosyncrasies and isolate the variance that can lead to a lot of statistical efficiency gains. So one of the symbols for this was the so-called Latin square design, where you get this matrix of assignments such that every column and every row has exactly one level of the treatment. So this is a really elegant thing, and this was commemorated by his college in this glass. It was really nice, but it had to be took down in 2020 because there's some protest against this. And then that's why there was this conference about him. And that's why I gave that talk, and then that's kind of leading to here. So you can still see that glass, I think, but this is kept in their library. What I wanted to discuss next is kind of what Fisher said about non-randomized studies or observational studies, which is what we care a lot about these days. This kind of started by this paper, Doe and Hill in 1950. So Hill, this is the same Bradford Hill. And there are many other studies around that period in 1950s that revealed a large and robust association between smoking and lung cancer. And this leads to a declaration by the British Medical Journal, and also similarly in the US, that basically there's a causal link between smoking and lung cancer, and perhaps people should not smoke. So Fisher kind of notoriously got involved in this, and he heavily criticized all the credibility of all these studies. He said such results suggest an error has been made of an old kind in arguing from correlation to causation, and blah, blah, blah. And he gave an explanation that smoking was probably genetically predisposed, so you're probably born to smoke. And he even provided some twin data to support the hypothesis that smoking is at least partly heritable. So this was a bit of a kind of a big controversy for him. One of the explanations was that he was himself a heavy smoker. He didn't want to admit this causal link, perhaps. But also, he was part of his research about this was supported by tobacco companies. So that was also perhaps, at least in the moral standards of today, that's unacceptable. But interestingly, there's also this a strand of literature that I got aware of from Dylan Small and Paul Rosenbaum, where there was an interesting quote on Fisher on observational study, which shows that he's not categorically rejecting observational studies. This is from a paper by Cochrane, reflecting on a conversation he had with Fisher. So Cochrane said, about 20 years ago, and asked in a meeting what can be done in observational studies to clarify the step from association to causation. So Ronald Fisher replied, make your theories elaborate. Right. So this kind of puzzled Cochrane, but what he said was that what Fisher meant was that when constructing a causal hypothesis, one should envisage as many different consequences of its truth as possible, and plan observational studies to discover whether each of these consequences is found to hold. So Fisher's idea of observational study is very, very kind of complex. You have to build a very articulated argument from these observational studies to support a causal conclusion. So he's a complex figure. He's saying kind of contradictory things in different pieces, but that's kind of very typical of Fisher. The other point I wanted to make a little bit was about this controversy between Fisher and Neyman, and I think that kind of had a role in causal inference today, and also how we discuss design. So Fisher and Neyman got into a really bad fight. I'm putting some kind of quotes here just to show you how worse it got. It kind of started from a discussion paper published by Neyman in 1935 about analysis of variance, how that is invalid for analyzing Latin square. And you can imagine Fisher wouldn't be very pleased with that. Then he kind of wrote the following. He said he was in the opening this discussion said he had hoped that Dr. Neyman's paper would be on a subject with which the author was fully acquainted and on which he could speak with authority. Since seeing the paper, he had come to the conclusion that Dr. Neyman had been somewhat unwise in his choice of topics. He would even go on even worse attacks. This is from Neyman's biography, which is an interaction between them after that discussion meeting in the UCL office. So I think apparently Fisher came to Neyman's office on one day, and then he said to me, so me is Neyman, he said to me that he and I are in the same building and he's going to this meeting, which is about Neyman's promotion to a professorship in UCL. And then I said, do you mean that if I'm here, I should just lecture using your book? And then he gave an affirmative answer. And I said, sorry, no, I cannot promise that. And then he said, well, if so, then from now on, I shall oppose you in all my capacities. Then he laughed, banged the door. So they are kind of, in the old days, I guess there's a lot of that kind of very strong personality and emotions. That's quite different from how we want to construct our academic environment these days. And one of the, I think, the thing that was probably just entirely unacceptable now is just this comment from Fisher after the World War II that importing from Eastern, that Neyman was importing from Eastern Europe his misconceptions as to the nature of scientific research. So Fisher is terrible at using kind of these languages, and he's just, I think, found him deeply disturbing in this level. But I wanted to get back to the scientific argument between them. Where is actually the difference? Is it just about kind of an incorrect analysis of Latin square, which actually about 10 years ago, there's a paper by Don Rubin and a student that shows there was actually a critical mistake in Neyman's paper, and Fisher kind of pointed it out using his intuition, but obviously he didn't find the mathematical error. So there's that side of the things. It doesn't justify attacking people this way. But what's actually going on was that Fisher had a history with kind of the Soviets, and also especially how genetics was done in the Soviet Union. So some people might know this Lyshenkoism, which is kind of a pseudoscience about genetics that was very popular in Soviet Union. So there is a bit of ideological differences here that Fisher has against Neyman-Pearson world theory. He's making some comments about Russians, and he said to conceal rather than to advertise the selfish and perhaps heretical aim of understanding for oneself of the scientific situation. And then he was saying something about thinking of our scientific problems in a language distinct from that of technological efficiency. So what's kind of going on is that Fisher's view of statistics and statistical inference is that it should serve a scientific purpose. It should help us do better science, which is about this kind of natural world that we know not very much about, and statistics should help that in that process. But the Neyman-Pearson world kind of decision theory type of approach thinks about kind of making the best decisions out of different choices using statistical data. And that's kind of the real differences between Fisher and Neyman. So Fisher indeed made some criticisms, a more scientific one in his 1955 book. He said he has three criticisms. of three concepts in Neyman-Pearson theory. This one is the repeated sampling from the same population, errors of the second kind, which is about statistical power, and inductive behavior. So the first point is actually not new. In this 1922 paper where Fisher developed the maximum likelihood estimator, he offered this remark about the postulate of a randomness thus resolves itself into the question of what population is this a random sample, which must be frequently asked by every practical statistician. So he you can see he's not going to be very happy with that assumption. But the main difference really is about the inductive behavior. So Fisher likes to think about his randomization gives a way to justify inductive inference, and the Neyman-Pearson theory just justifies inductive behavior. So those are two different things, and eventually both of them consider that as both Fisher and Neyman consider that as their main point of disagreement. And I thought this difference is still very much alive in causal inference. There is one brand of causal inference which I think was mainly about scientific discovery and hypothesis testing. There's another branch that's more about maximizing prediction accuracies when we change environment and how to optimize policies. For example, in online A/B experiments for these technological companies. There's also the difference between causes of effects versus effects of causes, which is a little bit like the inductive inference versus inductive behavior. Then for the last part, I wanted to move to kind of the design principle and how much of we have achieved in that direction. So there's a lot of kind of progress and ongoing research in statistics since Fisher's time, and they're all very closely related to the concept of design. So causal graphical model is a great example. The graphs are used to kind of help us see what's happening. You can say causal graph is a really nice design for causal inference. Or the identification of causal effects, all the different ways we do it, G formula, backdoor, front door, ID algorithm, instrumental variables, negative controls. These are all kind of ways we design a study. Design-based statistical inference is basically a modern rephrasing of randomization inference that emphasizes that we only use the information in the design in our statistics, or in our inference. The numerous innovations in clinical trial designs, adaptive experiments, and their statistical inference, target trial emulation, triangulation, and evidence factors. There are even non-causal things like missing data. I heard about from Ilya last week. That's about design. That's kind of a defect in the design, and we have to do something about it. And kind of moving away a little bit from causal inference is also the selective inference literature, which looks at the effect of selection, which is a kind of design. It's part of how the data are collected, and you need to consider that in your statistical inference. So there's a lot of progress, and the kind of analogy I wanted to draw is with a marble boron. So I visited the Young V&A Museum a couple of weeks ago with my child, who's a 4 or 5-year-old. And there was this game in that museum, in the play gallery, which I thought really had some similarity perhaps with where we are. So it's a giant magnetic board on both sides, and then you can put these kind of tracks to guide the ball running. And this is a little bit different from the usual marble boron, because what's nice is that there's some holes in this, and if the ball goes there, you can go to the other side, and then you have to really think onto both sides. And I thought maybe, can we think about causal inference as also kind of building that? As we have an enormously complex system that we want to study with some statistical data that we collect. And then when we think about that, there's an important part of the design is that the problem has many sides, and we kind of need to this ball, if this ball is where we are with the problem, we want to kind of design the tracks and guide them to go to the right place and then maybe it goes to the other, flips to the other side, and then we design the tracks over there, and it goes to the other hole, and then it comes to the other side again. So there is a little bit of I think a lack of emphasis on design in causal inference and also in the whole kind of data science. We tend to think about what kind of the fancy methods, machine learning, AI methods actually these days can be used on the data sets, and then that can do wonders. But we don't tend to think so much about how the data sets come from and what data actually needed, what new data should be collected. So that's what I call the design principle, which is how data are collected and pre-processed are crucial in the interpretation of any results from a statistical analysis. I think many people are converging to this from many different directions, and this problem is even more so important with the advancement of technology and hopefully relatively AI safe as a research area, because it's really about how humans interpret their statistical analysis. And this is such a big area, so many open problems, and that requires expertise across discipline. So I look forward to talking to you in this program and developing this in the program. Thank you. We have 8 minutes, so I can take questions from here or online. From here, check online maybe. Odd.
No, sorry, I was waiting to Jamie. So.
You want to say something, Jamie? Yes.
Yeah, thanks for the talk. I was curious whether, based on what you told us about the history of Fisher's research, there was already like a hint about transfer learning among different domains. He studied agriculture and genetics and healthcare, like how we could, borrow from experiments in one domain.
Well, I guess that's the beauty of mathematics. Somehow, real-world problems from different domains, they all can be kind of addressed with the same mathematical theory and principles. I don't think Fisher really did much work for health or medicine, apart from this probably counterproductive effort at opposing smoking has an effect on lung cancer. But there's definitely that kind of a shift from, he was mainly just working on genetics and the mathematical tools for that. Then he was hired as a statistician to look at agricultural experiments. But then you see that it may be a coincidence, but the mathematical tools are very remarkably similar. The analysis of variance developed for genetics would apply to the analysis of variance for agriculture experiments or other experiments. So I guess that's why we're here in this institute to talk about not just the applications, but also how those applications are connected. What's the underlying mathematical framework for all of them? Yes?
So one basic question, just as a conversation starter, and there's no right answer to this, but some perspectives would say that randomization is not part of causal inference. Causal inference is just about observational studies. I would say actually a randomized controlled trial is also causal inference. It's just a really convenient one. Do you think that's relevant, or given that you've just given a talk on randomization?
No, I would disagree. I think certainly we draw a lot of insights about observational studies from randomized experiments, both historically and now. And to me, I would define causal inference as anything, well, if your goal is to obtain, like to infer some causal relationship, I would call that activity causal inference. So whether that's using experimental data or observational data is a bit of a secondary thing, because like, why do we want to exclude the randomization people or the clinical trial people from our community? It's I think I would say we should be more inclusive and try to make this as large as possible, as broad as possible. Yes.
So yeah, no, this might fit our discussion more than just a question. So I was looking at your almost exact Mendelian randomization paper, and you have 5 loci, which is almost as chromosome translocations. So I think a big problem is because we had a mutation and we had a big, phenotypic difference. We don't focus on a real problem. So we pay a lot of attention on randomization, which is never the case. I will give you an example to explain what I'm saying. Is let's say have a spark in London Underground, and a train accident happens, and the whole the city bursts out. So that's the phenotype you are seeing at the level of London, but it actually happened because of a spark, which is your loci, which are level at the level of DNA, which you can already monitor. Because how the people work, and we are still stuck with the Mendelian things. We pay too much importance on formalization of randomization than actually looking why that loci had a mutation, and if that mutation actually led to the whole city being destructed. So as I said, this is more for a discussion than a question, but I think like a lot of times as data scientists, we don't actually understand the data, and as mathematicians, statisticians, we are totally clueless what exactly the meiotic process is, as compared to what your figure shows is chromosomal translocations. So I think another example is there are hardly any advancements in cancer, to be very honest, right? People do sequencing, but most of them actually don't understand what's happening really. So yeah.
I have 2 responses. The first is what you said is very similar to this kind of inductive inference and inductive behavior and causes of effects and effects of causes kind of difference. The other one is, I think you know more about the data than the mathematicians and statisticians. This is coming back to the previous question. The mathematicians would see commonalities of problems in different fields, but they do not know the particularities, because every field, every data set will have their particularities. You will know, as the people who actually collected and got the data, you will know how they're collected and pre-processed. We not necessarily would know. What I would like to work towards was people like you who have the scientific problems, and people who are statisticians, like a lot of the program participants here, to come together and say, well, let's not start with the model that you got in the data somewhere, and then you ask us to analyze it. Let us work before you collect your data, so you can talk to us first about what data actually need to be there to answer your problem, and then we work sort of along the way. So that's kind of what.
I think
ideally what I would.
I think my broader point is biologists will never really go on and really learn the maths, and I think on the other hand, I think we are so much happy in our niche that we are working on this algorithm, this thing, that we really don't put the effort to understand the biology. I think it's much easier for physicists and biologists to really dig deep and really solve the problems than the other way around. But another point is, a lot of these things are really deterministic, and we don't. I think, sincerely, I have worked with so many scientists that very few people really put the effort that is required to see what's actually happening. Like your magnet thing, right? The holes in that, and you design, so really pinpoint.
Yeah, so that's why I think we require really interdisciplinary conversations. So please come along to this program, and we can have a deeper, longer conversation. Maybe we'll just take one more question, because there's sorry, maybe a couple more questions, then we must stop. Okay.
I just had a historical curiosity.
Yeah.
So the paper from Wright and the paper from Fisher, they were more or less around the same time. Was
Yes.
there any direct or indirect contact between the two theories? And the
I
other
don't
one
expect anything other than they just see each other's paper. Because Wright was in the US, and I don't think, well, I'm not a historian, so I didn't study everything about them, but I don't know if there is a kind of a personal correspondence between them. I would doubt so.
And the other one is, so you mentioned Fisher and some very controversial positions on human genetics topics. And historically, did this happen before his focus on genetics and randomization in agricultural studies, or would it happen later?
Okay, so it's complex. So there wasn't really a genetics. There's the Mendel, and then people rediscovered his work. And then there was a social movement along, in the early 1900s, which kind of coincided with this idea of eugenics. So you can kind of getting better birth. So you have better people. How do you describe it? But that was kind of very popular, both as a kind of a philosophical, political idea, and also in academia. So people who are working on genetics, they would just say they're working on eugenics. And then obviously after a while, especially after the World War II, this has become, extremely unpopular. And I think what was very controversial was even after the World War II, Fisher kind of still tried to defend eugenics. You might have some point that eugenics in the early period and in how it's understood later were a little bit different. But then there were certainly some things that he did was not unacceptable. Was unacceptable. I don't know that part that well, but this conference organized by the Keys College, I think they have recordings online. And I was there, and there were some amazing historical talks. So I recommend those to you. Yeah, just one more question.
Yeah, so there are three purposes of randomization explained. So one was randomization provides basis for applying statistical tests. So what exactly means, especially in trial setting, clinical trial setting? Is it the same like we can apply statistical test if all the observations are identical and independently distributed? Is it the same or something else?
No, so there are 2 points. One point is you can kind of look at the randomization of a test statistic, then you can construct the exact test. So Yao will talk about that. There's a second point, which is in some problems, randomization would create a symmetry that would then allow the test to have an approximately normal distribution. That's a second point. So yeah, that's both points were made by Fisher. He kind of backed out a little bit on the first point about the exact test. He was a bit unsure about whether he actually never wanted people to use the randomization test as it's described as a physical act of randomization. He said, well, if you just do an experiment and then just analyze with my analysis of variance, then you're good. That was his main recommendation to practitioners. I don't know if that still stands for any more complex experiments anymore, but kind of backed out a little bit on the kind of actually drawing random numbers again and doing the exact randomization test. It's also not possible in his time. They don't have a computer, so that's maybe why he didn't like that. Okay, but I think we must stop. We're already over time.